welcome back. So let's talk about in-band full duplex. So the title today is in-band full duplex radio for integrated access and backhaul. I told you about integrated access and backhaul. This is the one of the 5G scenario that introduced in release 16 and release 17. And then integrated sensing and communication. This is a very active research in 6G networks. Okay, so the story is I'll tell you about in-band full duplex radio, and then you can see this in-band full duplex radio is ideally suited to these two scenarios. One is integrated access and backhaul, and other one is integrated sensing and communication. Okay, so. So this is the kind of a overview of my talk. I'll start give you some motivation and challenges for belong 5G and 6G network. Then I'll talk about what is in-band full duplex communication. To realize in-band full duplex communication, we need to cancel self-interference, which is the very challenging task. So we will spend more time on what is this self-interference is and how to cancel this one, etc. Then, as I said, in-band full duplex radio is ideally suited for these two applications, which is integrated access and backhaul. This is the 3GPP scenario in release 16 and 17 they introduced. Then I'll talk about in-band full duplex IAB integrated access and backhaul transceiver design and some simulation results. And then I will briefly mention about integrated sensing and communication and transceiver design, etc. So I think we have talked about this one in the first day. In 5G, there are three scenarios. One is enhanced mobile broadband service. The enhanced mobile broadband service is achieved by using massive MIMO technology, and then massive machine type communication. And this future of 5G is still not very much deployed. I think they will be maybe deploying currently at the first 5G deployment. They only consider enhanced mobile broadband service with the 5G massive MIMO technology. Still, the massive machine type communication is still using, at the early stage, they use the narrowband IoT, etc., which is the 4G technology. The 5G machine type communication is, maybe happening now. And the ultra reliable low latency also, is not deployed at the beginning of 5G deployment, maybe happening now. Okay, so the 6G. I already mentioned this. This enhanced mobile broadband is further enhanced to terabits per second service. Massive machine type communication also enhanced to accommodate more devices are connected into particular geographical area, and the ultra reliable low latency also reduce the latency from 1 millisecond to 0.1 millisecond. And then the sensing, the future base station in 6G, they not only communicate, they also do sensing the environment. So they, the previously sensing is used by radar system, and they also need a spectrum. And then our base station also need a spectrum for communication. So, so this radar system and the communication systems are fighting for spectrum. So now in the future, we like to see the radar sensing and the communications are integrated together, share the spectrum efficiently. So that's the plan for 6G. So sensing and communication are integrated together. And we also will see the AI, artificial intelligence and machine learning play a crucial role in the 6G network. So so that's, I already mentioned all these things in the first day as well. So anyway, so the 6G have 6 pillars, native AI, 6G hardware and the software will be supported by artificial intelligence. which enable intelligent end-to-end communication links and distributed learning. The challenge here is to reduce the computational and communication cost, training overhead, etc. Network sensing, as I said, in 6G era, radar systems are expected to be integrated with the communication system to achieve a single advanced system called integrated access and backhaul system. Okay, integrated access and integrated sensing and communication. Okay, so the radar system use need a spectrum, and our communication system also need a spectrum. They are currently disjoint system. We like to bring together and share the spectrum and the hardware and etc. efficiently rather than two separate hardware, two separate systems. So that's the plan in 6G. Okay, in 6G era, radar system are expected to be integrated with the communication system to achieve a single advanced system called the integrated sensing and communication. So there are a lot of research is going on in the integrated sensing and communication. So that may be one of the topic. If you wanted to do PhD, you can have a look at it. Extreme connectivity, peak data rate of 1 terabits per second we expect to deliver in the 6G. The latency is reduced to 0.1 millisecond. Network capacity of 10 million devices are connected in 1 kilometer per square. That's the objective of the 6G. And another objective is integrated terrestrial and non-terrestrial network. I told you before as well, to provide 100% Earth coverage, we need to integrate terrestrial and non-terrestrial network. The terrestrial network is the current our 5G system. Non-terrestrial network is the satellite system, etc. So 6G will make the unconnected in 5G will be connected in 6G. So whatever is not connected in 5G, the objective is to connect them in 6G. So yeah. VLEO is mean very low orbit satellite, VLEO satellite. So this kind of a constellation, if you put them around the Earth, we will be able to provide service. The current LEO satellites are very, very far away. So then it's take low, there cause a latency issue. So we need to put a satellite constellation very close to the Earth. So that's called VLEO to reduce latency compared to satellite comm. Okay. So if you put a very VLEO networks, they also increase the coverage and localization accuracy as well. And the trustworthiness and the security is another issue in the 6G, and the sustainability and the green network design is also another challenge. So these are the 6 pillars of 6 area the people are working on. This view of 6 pillar is Huawei view. Actually, this is a Huawei point of view. These are the 6 view they introduce. It's a bit different than the one I talk on Monday morning, which is IMT 2030 view. This is Huawei's view. Okay, so I'm going to talk about the in-band full duplex communication. So what is in-band full duplex communication? Okay, so that's what I'm going to explain to you. Okay, so currently all the commercial communication system are operating in the half duplex mode. I told you about that yesterday as well. Half duplex mode is the one currently all the communication system are operating. That means the uplink and the downlink are communicated orthonormal fashion. One is TDD, other one is FDD. So these are the 2 fashion uplink and communications are happening. So let's talk about the half duplex communication. So here, this diagram, I'm showing a base station. So even though I'm putting some of the antennas here, they are receiving the signal. Some of the antenna here, they are transmitting, but they can be a same antenna, okay? So, but for the explanation, to make things easy, I put some of the antenna here they are receiving, some of the antenna they are transmitting, but they can be a same antenna, okay? So there are some uplink mobile users wanted to communicate to the base station. The base station also wanted to communicate downlink, some of the downlink users. So what is, so there are two mode, TDD and FDD mode. I told you they are uplink and downlink is happening orthonormal fashion, okay? So currently, all the system operate in half duplex mode. Uplink and downlink operate orthonormal channel. The time division duplex and frequency division duplex. So uplink can happen in a different time, but the same frequency, but downlink can happen different time at the same frequency as well. So that is called TDD. And uplink can happen, downlink can happen simultaneously, but different frequency. That is going to be FDD. But full duplex mean we need to do uplink and communication same time and same frequency. That will double the spectral efficiency. So that's the objective. So it's not easy to implement. That's what I'm going to tell you the story, okay? So you can see here, the uplink, so I'm going to explain about the TDD system. Uplink is happening at time 1, but use same frequency, and the downlink is happening at time 2. So this is TDD, okay? They use same bandwidth, but different time, okay? So that's the TDD. So this is a time division duplex. The uplink happening at particular time, the downlink happening a particular time, but all the full frequency is used for uplink and the downlink. So this is the TDD system. So you can immediately see the waste time resources, because we wanted to use all the time for uplink, all the time for downlink, all the frequency for both as well. So if you do that, we can double the spectral efficiency compared to TDD system. Another wasted time resources and switching interval between uplink and downlink. So there's a wastage of resources as well. So let's talk about FDD. So FDD, uplink and downlink is transmitting at the same time, but different frequencies. They are here F1 and here F2, different frequency. So it is going to be like that. You know, your frequency is divided, and some of them for uplink, some of them downlink. Again, you can see a waste of frequency resources. There's a guard interval as well. We like to use uplink and downlink and same time and same frequency. So that is the objective of full duplex. So in-band full duplex communication, we do uplink and downlink, same time, same frequency. So that's the plan. So if we do that, there is a two big problem. That's why currently there's no full duplex system is deployed. So what is that two problem? What happened is there is a self-interference. So if you transmit same time here, same frequency, and you also listen same time, same frequency, there is a self-interference. When you transmit, you will transmit at very, very high power to downlink users. You are also listening from the uplink users. So this transmitted signal will cause interference here because you are transmitting same time and same frequency. So this is kind of an analog to, you are shouting and you are also trying to listen somebody's whispering. So it's like that, okay? So because you are transmitting mean you are shouting, and also you are listening somebody's whispering. This is because this is coming from very, very low signal to noise ratio. So so that's the that is cause problem. So there is a self-interference, then you need to cancel. So if you cancel this self-interference, that you are the one transmitting, you know what is transmitted, but you will be able to, if you are able to cancel that self-interference, normally that self-interference is around 120 dB or something like that. It's a huge self-interference. So if you can cancel that, then you can transmit and receive same time, same frequency. You can double the spectral efficiency compared to half duplex system. So another challenge is the, if these two guys are transmitting and listening same time, there is a co-channel interference between uplink and downlink users as well. So because of these two interference, there is currently no full duplex system is deployed so far, and this is, these two challenges can be addressed, and in 3GPP, the IAB scenario, integrated access and backhaul scenario, 3GPP mentioned full duplex can be a potential candidate. So what is integrated access backhaul is, I told you, there is a IAB node, integrated access node here, and there's a base station here, G node B. And it will send information to this guy, because we need, for the millimeter wave frequency, we need to extend the coverage by using IAB node here, and these guys will serve users here. So the integrated access backhaul mean this is doing access, this guy, and also listening data from the backhaul as well. So these both are wireless, So this is ideally suited for full duplex. You can transmit and you can also receive. So this guy can operate in-band full duplex mode. Okay, so that's what 3GPP mentioned. Potential application of in-band full duplex is integrated access and backhaul. Okay, so this guy will, this guy is called IAB node. It will serve the users. It's kind of a millimeter wave coverage extension relay kind of node, and it's also connected to the IAB donor. We call G node B or IAB donor or base station, whatever we can call, and that will give access to this data to this IAB node, wireless access. They are not wireline. So yeah, so we can use a integrated full duplex technology here. Okay, so anyway, so let's talk about the remaining next half an hour. Is I will be talking about how to cancel this self interference. Okay, this self interference is like a 120 dB. Different dB strong, we need to cancel. Okay, no transmit and receive simultaneously on the same frequency, time, and slot, and up to twice the throughput. No additional transmit power or bandwidth. No waste of time or frequency resources. Okay, so full duplex is happening like this. Okay, you are using the same bandwidth, same time for transmit and receiver. Okay. But the fundamental challenge is the high self-interference cancellation. Signal emitted from the transmitter, this guy's antenna node is receive its own receive antenna. Okay, and because of this, because of the large interference, what happened is it will, you can immediately think, I am the one transmitting signal here. I know what I am transmitting. So if we, from here receive signal, if I subtract this whatever I transmitted, then then I will be able to receive this one. That's intuition that you will see. I know what is transmitted. If I subtract it from the receive signal, the self-interference is cancelled. But it is not that easy, because of this larger power that you are transmitting, that will saturate your receiver. Okay, so saturate the front end of the receiver, and simple subtraction concept cannot be applied here. So that's what I'm going to show you. Any question? Yeah. Yeah. For example, in the cellular system, some of the users are sending information, some of the users are receiving information.
For example, I am a cellular.
Oh, yeah.
I transmit and I get it.
Yeah, yeah.
So I am using a full duplex channel.
You are transmitting. Okay, yes. In that case, yeah.
So in that case, how you subtract this powerful signal from weak signal?
Yeah, that's what I'm going to explain to you. Yeah. So so here, this guy is the full duplex. These guys are still, we thought, we are treating these users as a half duplex system. Okay. Yeah. So only the base station is the full duplex. Okay. Okay. Because you need a strong signal processing techniques need to be applied. So base station is the one full duplex. Okay. Okay, so some example scenario for in-band full duplex. So here is the kind of a full duplex base station. Is receiving signal from here. It is also receiving signal from here. It is transmitting here. So here it's like this. Okay, so it's these guys is a half duplex. So these are transmitting, this guy is receiving, and this guy also transmitting to this user. So this is a full duplex uplink and downlink cellular system. And here is the both are full duplex. Here is the both are full duplex, maybe a point-to-point IoT device or device-to-device network. Okay, so here is the self-interference. This own transmitted signal is going to the receiver. This is a self-interference, and this is a self-interference. Okay, the blue signal is self-interference. The black one is signal of interest. Okay. So, so let's talk about this self-interference. This self-interference from the own transmit antenna to receive antenna is very strong compared to signal of interest. So, signal of interest is this guy. This guy is a signal of interest. This is a self-interference. So the self-interference is very strong compared to this signal of interest. So for this guy, this is the signal he wanted to receive, but this is the interference because of this guy is transmitting to somewhere else. Okay, so that's the self-interference. So it's around 80 dB or maybe 120 dB, etc. Solution in theory, the interference, this interference signal. Is known, as I said, already, this transmitted signal, same node is transmitting, so the interference signal is known here. The strong interference dominated regime, the channel estimate, if we can estimate this channel, we can subtract from the received signal. That is the intuitive solution, but that is not going to work. I will show you in a minute because the strong self-interference will saturate this receiver and the receiver is unable to receive the desired signal. So, yeah. So this is the normal transmitter and receiver chain here. So, so I will explain to you in a minute. So the self-interference will come here. We do an analog to digital converter at this point. And before the analog to digital converter, we need to cancel this self-interference, most of the self-interference. Because after analog to digital converter, things are become difficult. Okay, so let's talk about it. Okay, so here is the received signal here the received signal here consists of this desired signal, the black signal, and the self-interference signal, okay, the blue signal. So the black signal is, here because this user is very far away, so this is very, very weak signal. So that's why the black signal is very, very weak. The self-interference is very strong signal. The blue signal is very strong, and black plus blue will give you the red signal. Okay, the red signal, the received signal at this point is red signal, which consists of this black signal and the blue signal as well. So the blue signal is the self-interference that we need to cancel. We need to cancel, and we need to then, if we cancel properly, we can extract the black signal. So as I said, we need to cancel this self-interference before we do analog to digital conversion. So after quantization, you will get this kind of signal, and if you subtract after removing the interference, okay, after removing this blue signal, what you are getting is kind of a quantization noise, okay. If you do it in the digital domain, after you do the, after quantization and after removing that interference, what you will get is a quantization noise, and from this guy, you won't be able to. So the, after you do analog to digital conversion or after quantization, if you remove this signal, this blue signal, and then you will get this signal which is hopefully the corresponding to this signal, but from this one you won't be able to decode because this is just a quantization noise, okay. So after analog to digital converter, the desired signal saturate, get only 1 to 2 bits of resolution, cannot be decoded, okay. Usually the receiver need at least 6 bit of resolution. Okay, so this intuition of what are the signal that we transmitted, we know. Why don't you subtract at the digital domain? This kind of self-interference cancellation is not going to work. Okay. So in real life implementation, strong self-interference must be mitigated in analog domain before analog to digital conversion. Okay, before the analog to so we need to cancel this self-interference before we do analog to digital conversion. So we will do some kind of antenna cancellation, analog cancellation, etc. Then we will reduce the self-interference as low as possible. Then we do the remaining self-interference in the digital domain. So we need to bring the self-interference below the saturation region of the receiver. So that's what, to do that, we need to do analog domain cancellation before the analog to digital converter. How much interference need to be canceled, how to cancel. So, okay. So let's consider 2 scenarios. So I would like to explain 2 scenarios and tell you how much self-interference that we need to cancel. So let's say there are 2 scenarios, small cell scenario and Wi-Fi scenario. So 2 scenario here. This is the transmit power, 20 dBm, and in the small cell scenarios, and the Wi-Fi scenario also, let's say 20 dBm. Okay. And the power of the received self-interference, this self-interference is, let's say here is 5 dBm, and the Wi-Fi also 5 dBm, okay? And the noise flow, let's say the noise flow here is in the small cell scenario minus 100 dBm, here is minus 90 dBm, okay? So, let's, the signal, this signal, signal of interest is very, this user is very far away, so this signal will be minus 80 dBm, and here also minus 80 dBm. So what we need to do is we need to bring this guy, this self-interference below the noise flow. Okay, we need to cancel. This is 5 dBm, this is minus 100 dBm. So we need to cancel almost 105 dBm cancellation, bring this self-interference below the noise flow. Similarly, we need to bring this guy below the noise flow. So that's the, if we do that, we can enjoy the in-band full duplex benefit, okay? So we need to cancel here 105 dB required cancellation to bring the self-interference down to the noise floor, okay? Similarly, here in this scenario, Wi-Fi scenario, if we use full duplex, we need to bring this self-interference 95 dB self-interference cancellation we need to do to bring the self-interference below the noise floor, okay? If we don't do that, what happened to our, if we don't do that, our signal to interference plus noise ratio is minus 85 dB, and you cannot communicate at minus 85 dB any communication. So without self-interference cancellation, the signal to interference plus noise ratio is minus 85 dB. With minus 85 dB, you cannot do any communication at all. So here is also, if you don't cancel it, your signal to interference plus noise ratio is minus 85 dB. So we need to cancel. So receiver in-band full duplex system useless such a SANR. This SANR is useless, and this is called self-interferent dominated over noise. Okay, but if we can cancel the self-interference, okay, if we can cancel the self-interference here, if we can cancel the self-interference and bring it to noise flow, similarly, if we can cancel the self-interference and bring it to the noise flow, then we end up with a noise dominated over self-interference, and signal to, if we can cancel it, the signal to interference plus noise ratio is around 20 dB. So this is a good signal to interference plus noise ratio, and you can do communication. Okay. Similarly here, if you can cancel the self-interference more than 95 dB, your signal to interference plus noise ratio is 10 dB. 10 dB is a good signal to interference plus noise ratio for communication. So yeah, so you can see in the small cell scenario, we need to cancel this guy 105 dB. And here is 95 dB we need to cancel. So we cannot use a particular technology only to cancel this one. We are going to use 3 technology here. One is antenna cancellation, analog cancellation, and the digital cancellation. 3 way of cancel, 20 dB, 30 dB by antenna cancellation, another 20, 30 dB by analog cancellation, the remaining 30 dB by digital cancellation. So we do a 3-domain cancellation. Okay. So large amount of self-interference cancellation required to mitigate the SI to below the noise flow. Small cell scenario, more than 105 dB SI cancellation is required. The Wi-Fi scenario, more than 95 dB of SI cancellation is required. With the network densification, I talk about network densification is one of the technology in the 5G to bring the base station closer to the user. If you do a network densification, then you can transmit less power compared to the original power. If you transmit less power, your self-interference also will be reduced as well. So that is another advantage. If you do a network densification, the transmitter power will be reduced, so the self-interference also reduced, so the cancellation load will be reduced. Okay, so the gain of full duplex over half duplex depends on amount of self-interference cancellation. So if we can cancel only, we will enjoy the double the spectral efficiency benefit. If we don't cancel it, then half duplex is better than the full duplex. That's why so far the half duplex is the one deployed all the communication system. Okay. But hope to see a in-band full duplex communication in 6G is some of the application like this IAB. Okay, so we did a project with Huawei doing millimeter wave IAB network to cancel this self-interference cancellation project before. Anyway, so here is the kind of a in-band full duplex terminal here. You can see here, this is the transmitted bit here. Transmitted data is going here, and it is transmitted to some users here. And so the self-interference, this transmitted signal is going to receive here your own receiver. There will be a direct path coming here, and also it will be some reflected path also going to come here. So we need to cancel everything together. These redded signal are self-interference. There will be a direct path. Maybe we can cancel it by putting some some absorbing material or some kind of beam forming, etc. we can do to stop the direct path. But there will be some reflected path also going to come and cause self-interference as well. So yeah, so that's the problem of this self-interference cancellation. So I talk about, so this is, you can do some absorbed material can be put between transmitter and receiver, etc., to stop some direct path, or you can do some transmit beam forming such that that radiated energy is not going in this direction, etc. So this is kind of an antenna kind of cancellation. Okay, there's another analog cancellation. There's a circuit here, analog cancellation circuit. What is this circuit is doing is they taking the signal from here before the transmitted signal antenna, and then it will mimic this self-interference channel is created here and then subtracted before analog to digital conversion. So before analog to digital conversion, we need to cancel as much as self-interference as possible. We do it in the antenna domain, we do some absorption material in between, and we do some analog cancellation before analog to digital conversion, etc., such that the strong self-interference won't be saturate this receiver. Okay, if we don't do this self-interference cancellation, this receiver will be saturated because it's a strong signal, and then you don't have, you cannot do anything. So we need to cancel all these interference antenna domain, analog domain, such that the strong self-interference is not going to saturate this receiver. Okay, so we need to cancel in propagation domain or in the antenna domain. Analog circuit, this is the analog circuit cancellation. You take the signal here and mimic the self-interference channel here and subtract before analog to digital conversion. This is analog cancellation. And then the remaining will be deal with the digital domain. Okay, the remaining residual self-interference we can do cancel at the digital domain. So this is the kind of a, so we do, let's say, 30 dB cancellation here, another 30 dB cancellation here, and remaining 30 dB or 40 dB cancellation there. If you do it, then you can enjoy the full duplex benefit. Any question? So that's the plan. So combination of antenna cancellation, analog cancellation, and digital cancellation will lead to this 110 dB or 105 dB cancellation. So people have demonstrated this one. By doing so, you will be able to cancel the self-interference and able to enjoy the full duplex benefit of doubling the spectral efficiency. Okay, doubling the spectral efficiency is a huge benefit. You know, some early work people consider, you know, there's one transmit antenna here at distance d. This is the receiver antenna. If you put another transmit antenna plus d plus lambda over 2, then the signal will be, add destructively because these are lambda over 2 different. So this signal here will be destructively add together, and one kind of a cancellation can be possible. People have done many way of cancelling antenna cancellation. Okay, so anyway, two transmit signal. The two transmit signal, this signal and this signal, interfere destructively at the receiver to cancel, so the interference will be reduced. So this kind of techniques people have studied. Here is another technique. So this is called a balloon transformer. What is this will do is it will take the received signal here and mimic the self-interference channel here by finding the attenuation and delay of the self-interference channel, and then subtract from the received signal to cancel in the analog domain before it is changed to analog to digital conversion. So yeah, so you need to cancel majority of the self-interference before analog to digital conversion. So this is a kind of another analog cancellation, okay, analog cancellation techniques. Okay, so the remaining, if we do both analog and antenna domain cancellation, the remaining cancellation, you do it in the digital domain. So the digital interference cancellation, you can do it at the digital domain. Any question? So the residual self-interference, so after analog and antenna cancellation, the remaining residual self-interference will be handled in the digital domain. So that's what is shown here. The residual self-interference around 30 to 40 dB still exists that can be done in the digital domain. So depending on the strength of the residual self-interference, optimum transmitted strategy for half duplex system can be far from the optimum in-band full duplex system. The residual self-interference is not well handled. It is still prevent us from benefiting. So the residual self-interference is still we need to properly handle and eliminate, then only we can enjoy the in-band full duplex benefit. Okay, we can do many techniques to handle that residual self-interference by using beamforming, power allocation, etc. So next is self-interference cancellation techniques. Okay, so this is kind of a recap. I think you know all these things. Okay, so this is the kind of the power budget for in-band full duplex node. Okay, so here the signal of interest is this guy, and this is a strong self-interference, and this is a co-channel interference. Okay, so you can see here this is the transmitted power from the transmit antenna, and you cancel some of the self-interference in the propagation domain. Okay. Then you cancel the remaining self-interference in analog domain. Okay, so this is the cancellation in propagation domain. This is the cancellation in analog domain. Then your self-interference is going to come somewhere here, and the receiver dynamic range. The receiver dynamic range is here. So what you had to do is you need to bring the self-interference cancellation, self-interference signal below the dynamic range of the receiver. Then the receiver won't be saturated. So, so you need to bring the self-interference within the dynamic range of the receiver. So by doing propagation domain cancellation, analog domain cancellation, you bring it to here. So this is here. This is okay. If you bring it here, that is in the dynamic range of the receiver, then it won't saturate your receiver, and you can deal with the digital domain cancellation, etc. So here is the self-interference signal. This is a signal of interest here. Okay, this is the self-interference in dB, and this is the self-interference minus propagation domain cancellation. You are here, and then you do antenna analog cancellation. You are here. And then you need to do digital cancellation. So here I show you some noise flows. Okay, the receiver noise flow depends on the bandwidth. If you are using 10 megahertz channel, your receiver noise flow is -1 dBm, 91 dBm. If you increase the bandwidth to 400 megahertz channel, if you are in millimeter wave frequency, your 5G millimeter wave frequency can have a 400 megahertz channel. In that case, your noise flow is -75 dBm. Okay, so yeah, so if you do analog propagation, analog domain cancellation, you are here. Then remaining you do in the digital domain to cancel to bring it here. Then you will be able to detect the signal of interest. Okay, so that's this is the kind of explaining the power budget. Any question? Any question? Yeah? Okay. Yeah, so self-interference must be suppressed analog and antenna domain to bring it here in the dynamic range of the receiver. Otherwise, it will saturate the receiver. Okay, so people have done many research in this topic. Okay, review of self-interferent cancellation techniques. People have done propagation domain cancellation. There are passive methods. There are active methods. Analog domain cancellation also people have done in time domain, frequency domain. I'll tell you about some photonic assisted analog cancellation in a minute. And some, then the digital domain cancellation, we can use linear techniques, nonlinear techniques, and some receiver beamforming techniques, etc. Okay, so there are many research have been done to do this self-interferent cancellation in all these domains. So. So here is some example here, self-interferent, the interference in propagation domain mainly focus on minimizing the direct path. For example, this is the transmit antenna, this is the receive antenna. You can put some absorbed material here to stop this direct path from going from here to here. So this can be done, okay? So this is mainly to stop the direct path. And then there is some active approaches. This is the circulator that I was telling. The circulator I put here the two antennas, but it can be one antenna. The transmitted signal will go here in this way, and the receiver will go this way. So same antenna will do transmitter and receiver by a technique called circulator here. So anyway, so and then the transmit beamforming, also another techniques. This is the self-interferent channel. You transmit orthogonal to the self-interferent channel or in the null space of the self-interferent channel. By doing so, you won't cause that much of self-interference as well. So there are many there are a few techniques people have done to cancel as much as self-interference, okay? So transmit beamforming will be steer the beam to the narrow direction towards the intended node, reduce the self-interference, okay? Or it can also steer the beam to the null space of the self-interference channel to null the self-interference. So yeah, so there are, I will tell you about a little bit of this null space projection techniques, etc. Later on. So, so transmit beamforming is the one I'm going to tell you now. So we can do a transmit beamforming, the one I mentioned here, transmit beamforming or null space projection, etc. So what you do is you find a beamformer matrix V, which minimize this. This is the self-interference channel, HSI, and V is the kind of a precoder or beamforming matrix. So you find a V that minimize this H into V. Okay, so this is the kind of a it's called a null space projection techniques. Okay, so you transmit in the null space of the self-interference channel. Okay. So step one is to find the desired beamforming matrix to minimize the mean square error, MMSE. So this is the error of from the downlink users, and this is the error due to uplink users. So you sum both of these error and minimize these both of the error with respect to this V, the precoder, and then you find the precoder, and then then do some further processing and try to find the null space beamforming techniques. Okay. So we have kind of extend that techniques to a little bit further by putting how much self-interference that we need to cancel by putting some threshold here. So this is the some reduced complex beamforming techniques that we have proposed. So we have shown here, so this is the spectral efficiency versus analog self-interference cancellation. So this is the kind of a null space projection techniques people have used, and we have proposed some other techniques here which is performing better compared to the null space projection techniques. So yeah, so this is four users. Here users have two antennas, and here users have four antennas as well. So yeah, so these are the our studies of cancelling the self-interference by beamforming techniques. Any question? I think it's going to. I think that's all I wanted to say about. I'll skip this one. Okay, so I'll explain this one. So there are two architectures that people have proposed to cancel the analog domain self-interference. This is the techniques that people proposed at the Stanford University. What they did is they take the signal from here, and this is your self-interference channel, okay? And then they create this self-interference channel and then subtract from the received signal, receive RF chain, and they subtract it here. So this is the self-interference channel, including the reflected path, etc. That it will create it, and then it take the signal from the transmitted signal, and this is a self-interference channel, and then multiply that, and they get the self-interference is subtracted before analog to digital conversion. So there's another group at Rice University. They propose some different architecture. They take the received signal, they come up with the auxiliary RF chain and some DSP that will mimic the self-interference channel, and then they cancel it here. I think we follow this architecture, and in the Huawei project that I mentioned, we need to cancel self-interference for bigger bandwidth, like a 400 megahertz channel, because of the millimeter wave frequency. We come up with the techniques called optical domain cancellation. So because if you have a 400 megahertz channel, the channel is more frequency. There will be more taps and etc. is needed. So if we do this kind of microstrip based analog cancellation circuit, we won't be able to create a multiple tap channel. So what we did is we take this electrical signal and convert the electrical signal to optical domain, and we create this self-interference channel in optical domain. In optical domain, the losses are less, so we can have a multiple taps, etc. A large number of taps, like 80 taps, etc., can be created, and do the cancellation, and then change the optical signal back to electrical signal, and then cancel the self-interference. So that kind of a techniques that we proposed. So you can some plot here. It is cancellation performance versus tap, okay, for 70 nanosecond delay spread channel here. These different lines are for different bandwidth. So you can hear this is the 1 gig bandwidth channel. To cancel a reasonable amount of self-interference around, let's say, 30 dB, you need to have a lot of taps, okay, a lot of taps, 80 to 90 taps. So that kind of many taps cannot be created in the microstrip-based circuit. So we need to do kind of optical domain cancellation. So similarly, for example, the Jello is a 400 megahertz channel. To cancel like 40 dB analog cancellation, you need to have a 70 or 80, 90 taps. So that kind of many taps you cannot create in the microstrip-based analog cancellation. So that's the kind of a study here showing. This is bandwidth is 400 megahertz channel, but different delay spread are shown here. Again, if you have a larger delay spread, you need more taps, etc. So, I'll show you. This is our electrical domain, optical domain 5-array based cancellation. We are taking the receive signal, tap the receive signal, and change it to optical domain, and we are creating a different delays and attenuation, and making this is our frequency selective channel with many taps, and then we change the optical signal to electrical signal and then cancel it, okay? So, yeah, so this is one. And there's another techniques people used before as well. It's called fiber brigade based cancellation. Again, the transmitted electrical signal is taken and then converted to optical domain with the different taps here, and make the analog self-indifferent channel using optical domain, and then cancel all these things and get the electrical signal back here and subtract it here. Okay, so here the electrical signal is converted to optical domain and create the multi-tap channel here, self-interference channel, and change it to electrical signal and cancel it at the receive antenna. So this is the one creating the self-interference channel with a lot of taps that is needed in the higher bandwidth case. So this is kind of the lab we have done this kind of experimental work. This is funded by Huawei projects. So any question? I think I hope I explained to you about the full duplex benefits and the challenges of canceling the self-interference, and we need to cancel in 3 domain: analog antenna and digital domain. If you can cancel properly to bring the self-interference below the noise floor, we will be able to enjoy the in-band full duplex benefit of doubling the spectral efficiency. I think that's all I would like to say. Yeah, this is kind of this is a circuit here. For example, this transmit antenna is sending information to the user. That information is going to the receiver. This receiver can be a same antenna, but it can be different antennas as well. So this is the self-interference that we need to cancel. This is the receiver is receiving a signal from here. So the self-interference have a direct path and also some multiple reflected path. So this self-interference channel is created here in the RF canceller and then subtracted, and before we change it to digital analog to digital conversion. After that, you do the remaining self-interference, you do it in the digital domain. Again, so you need to cancel the self-interferent analog domain in an appropriate level. For example, this is a self-interferent channel, the signal, and this is the noise floor. You need to, here, this is a self-interference cancellation done from here to here. That is insufficient cancellation. And you also shouldn't cancel too much as well. If you cancel too much, then what happens is the digital domain cancellation become a problem. So you need to cancel the self-interference appropriate level such that the remaining self-interference will be canceled in digital domain. If you cancel more, you are unable to estimate the channel for self-interference channel properly, then you cannot do much on the digital domain. So you need to cancel appropriate level. So here is a too deep cancellation. You can cancel from here to here, that is too deep cancellation. Here is too less cancellation, and this is kind of appropriate level of cancellation. You bring it to this maximum tolerable strength. If you cancel up to maximum tolerable strength, the remaining can be dealt with in the digital domain. So there are a lot of technical details are there, okay? Yeah, so I explained to you this integrated access and backhaul is a nice application of in-band full duplex. So for example, in 3GPP, they introduce a scenario called mobile IAB. What does that mean is in the railway compartment, there will be an access point, IAB node, something like that. It is going to move the train when the train is moving. There is a donor or base station will give access to this IAB node wireless access through wireless link, and then this access point will serve the users inside. This is a kind of a scenario for mobile IAB network. So this guy can use full duplex technology because this guy can serve the user and same resources, frequency and time resources can be used for backhaul with the base station to get the data as well. So this is kind of a ideal scenario for in-band full duplex. So same resources is used in backhaul and used in the access, okay? So this is called access, is serving the user, and it will also connect it to the base station through wireless backhauling. So the same frequency time resources used for backhaul and access by using in-band full duplex. So this kind of nice scenarios for in-band full duplex. And anyway, I think I will stop here.
Yes, sir, TKM.
Yeah, TKM. Yeah.
So yesterday we were doing the simulation, this E1 in this section 2, where this P is in -525 dB, and this is the multi-user MIMO simulation. This is the rate for each user. There are two type of beamforming, MRT and ZF. We choose n equals to k equals to 4, n equals to number of antenna at the base station, k equals to number of users. And we compare three things, MRT, ZF and single user MIMO with water filling, okay.